Hello everyone. So this is a question from JEE Mains 2026 8th April Shift 2. Given below are two statements. Statement 1, the number of pairs among titanium plus 4, vanadium plus 2, vanadium plus 2, manganese plus 2, manganese plus 2, iron plus 3, and vanadium plus 2, chromium plus 2, in which both ions are colored is 3. Okay. So the first statement talks about, you know, color. Okay. So and there is statement 2. We have to choose which of them are correct, and the chapters involved is DNF block. Okay, so let's talk about statement 1. So statement 1 talks about color, and color is due to presence of incomplete d orbitals. Very important. So color is due to incomplete d orbitals. Okay, so when the ligands approach the transition metal ions, so let's say we have a transition metal ion or a transition metal atom. Let's say the ligands are approaching. Okay, so the otherwise degenerate, the meaning of degenerate is having similar energy. Okay, so the otherwise degenerate d orbitals of the central metal atom or the ion, they split into T2G and EG. Very important. Okay, so I will write that down. When ligands approach transition metal ion, otherwise degenerate, the meaning of degenerate is having similar energy, d orbitals, obviously the 3d orbitals in the case of our d block elements, they split into T2G and EG. So with respect to diagram, we can show it in this fashion. So in the absence of ligands, they will look something like this. So all of them dxy, dyz, dzx, dx square minus y square, dz square, all of them will have the same energy. The moment ligands come and approach them, these guys are not degenerate anymore. They split into T2G and EG. So we have 2 above and 3 below. So these two are collectively known as EG, and these 3 are collectively known as T2G. Okay. So electrons can jump from lower energy T2G d orbitals to higher energy EG d orbitals. Very important. Electrons can jump from T2G to EG, and the amount of energy to do this transition is obtained by absorption of light in the region of visible light. The amount of energy that an electron needs to jump from T2G to EG can be obtained, or it is similar to the energy that is possible to absorb in the visible region. Okay, so I will write this down, that electrons can jump from T2G to EG, and required amount of energy to do this is obtained by absorption of light in the region of visible light. So therefore, this is the reason why the compounds of transition metal ions are colored. Okay. Therefore, completely empty d orbitals will be colorless because there are no electrons to jump from T2G to EG. So the criteria for them to show color is that completely empty d orbitals, they are colorless because there are no electrons to jump from T2G to EG. So let's say that there are no electrons itself. So there is no one to jump from T2G to EG. So therefore completely empty d orbitals, colorless. Okay. Similarly, if we have completely filled d orbitals, again that is going to be colorless because no vacant d orbitals for promotion of electron. Okay. So in the case of completely filled d orbitals, again it is going to be colorless because no vacant d orbitals for promotion of electron. Okay, so for example, let's say that all the electrons here are filled in T2G and EG. So we cannot promote anyone to EG because there is no vacancy, okay, for promotion. Okay, so now we know the criterias in which they are not going to show color and also going to show color. So let's look at the pairs. The first pair that is given to us is titanium+4 and vanadium+2. Okay, so titanium's configuration is 3d2 4s2. Vanadium's configuration is, and obviously there is a inner core of argon. In vanadium also we have a inner core of argon. So argon 3d3 4s2. So therefore titanium+4's configuration will be just argon, and vanadium's configuration will be +2. Remove 2 electrons, so 2 from here. So we will be having argon 3d3. Right. So therefore, in this case, there are no d electron at all. Right. So therefore, titanium+4 is going to be colorless. And in this case, in the case of vanadium, sorry, this is +2. In the case of vanadium+2, there are d electrons and also it is partially filled. So therefore, d electrons are available for promotion, and also we have empty EG where it can be promoted to. So therefore, yes, vanadium+2 will show color, but they are asking us in which pair both of them they are showing color. So therefore, this is not the answer. Okay. The next pair is vanadium+2 and manganese+2. So the configuration of vanadium is 3d3 4s2. The configuration of manganese is 3d5 4s2. So vanadium+2, we will remove 2 electrons from 4s2. So therefore it will be 3d3. And manganese+2, we will remove electrons from 4s. So it will be 3d5. So therefore you can see this will also show color. This will also show color. So therefore this is one of the pairs in which both the species show color. So this is, yeah, this is one of the answers. Okay. Next we have is Mn+2 and Fe+3. The configuration of Mn is 3d5 4s2. The configuration of Fe is 3d6 4s2. So therefore Mn+2 we will remove electrons from 4s. So therefore it will be 3d5. And in the case of Fe+3, we will remove electrons again from 4s and 2 from here and 1 from 3d. So therefore it will be 3d5. And in this case also Mn+2 shows color, Fe+3 shows color. So therefore yes, this is one of the pair in which both the species show color. And the last pair is vanadium+2 and chromium+2. So we know the configuration of vanadium, that is 3d3 4s2. The configuration of chromium is 3d5 4s1. The configuration of vanadium+2 will be So we will remove 2 electrons from 4s. So we'll be left with 3d3. And the configuration of chromium plus 2 will be, so we will remove electrons from 4s and 3d. So we'll be left with 3d4. So therefore, in this case also, vanadium plus 2 shows color, chromium plus 2 shows color, because both have, partially occupied d electrons, which can be promoted from T2G to Eg. And therefore, this is also one of the pairs in which both these species show color. So therefore, there are 3 such pairs: 1, 1, 2, and 3. So statement A says that the number of pairs among this, and this in which both ions are colored is 3. Yes, this is a correct statement. True. Next, we have statement 2. Statement 2 says that the number of pairs among this, and this in which both are diamagnetic is 3. So this word is important, diamagnetic. Okay. So let's talk about statement 2. So on the basis of behavior in a magnetic field, substances are classified as paramagnetic, diamagnetic, and ferromagnetic. Those substances which are repelled by the magnetic field are called diamagnetic. Okay, very important. So those substances which are repelled by the external magnetic field that we have applied, so they are known as diamagnetic. Okay, and those transition elements which have paired electrons, in which all the electrons are paired, so they are diamagnetic in nature. Okay, so those transition elements which have paired electrons are diamagnetic in nature. Okay, so we have been given 3 pairs. The first pair is lanthanum plus 3 and ytterbium plus 2. Okay, so lanthanum's electronic configuration is xenon core 5d1 6s2. So therefore lanthanum plus 3 will be, obviously, so we will remove 2 from here, 1 from here, so we'll be left with a xenon core. So it is xenon, just the xenon core. And we know that in a noble gas, all the electrons, all the orbitals are completely filled, and the electrons in the orbitals are, all of them are paired. So therefore this guy is going to be diamagnetic. The configuration of ytterbium is xenon 4f14 6s2. So therefore the configuration of ytterbium plus 2 will be xenon 4f14. And obviously all the electrons are paired in xenon, and 4f consists of 7 degenerate orbitals: 1 2 3 4, 1 2 3 4 5 6 and 7. And one orbital can accommodate 2 electrons of opposite spin, so therefore 7 f orbitals can accommodate 14 electrons of opposite spin, so therefore it is completely filled and also paired. So therefore in the case of ytterbium plus 2 also, it is diamagnetic. So therefore, yes, this is one such pair where both of them are diamagnetic. Next pair that is given to us is lutetium plus 3 and cerium plus 4. The configuration of lutetium is xenon core 4f14 5d1 6s2. So therefore lutetium plus 3 will be, so we remove or knock out electrons from 2 from here, 1 from here. So we are left with xenon core and 4f14. So therefore again xenon completely filled and paired, 4f completely filled and paired, so it is diamagnetic. Then we have cerium. The configuration of cerium is xenon 4f1 5d1 6s2. So the configuration of cerium plus 4 will be, we remove 2 from here, 1 from here, 1 from here, so we will be again left with a xenon core. And in a noble gas, we know that all the electrons are completely filled and paired, so it is also going to be diamagnetic. So this pair also contains both the species, diamagnetic species. And the last pair is actinium plus 3 and lawrencium plus 3. So actinium's configuration is 6d17s2. Obviously, there is a radon core, and when we remove 3 electrons, we are just left with the radon core. So therefore, the configuration of actinium plus 3 will be radon. And in a noble gas, all the electrons are completely filled, orbitals are completely filled, and all the electrons are paired. So therefore, this is again going to be diamagnetic. The configuration of lawrencium is radon core, 4f14, 6d1, 7s2. Therefore, for lawrencium plus 3, we remove these 3 electrons. So we'll be left with radon core and a completely filled 4f orbital in which electrons are completely paired. So therefore, this is also going to be diamagnetic. So lawrencium plus 3 will look something like this. So therefore, this is also diamagnetic. So therefore, yes, all the 3 pairs that is given to us in both are diamagnetic. Okay, in all the 3 pairs, both the species are diamagnetic. So let's look at statement 2. The number of pairs among this and this in which both are diamagnetic is 3. Correct. So therefore, statement 2 is also true. So therefore, statement 1 is also correct. Statement 2 is also correct. Both these statements are correct. Okay. Thank you.